Okay, so now I will present what I think are the main idea. So first to say that, so I need to recall a theorem of Benoit. I will call it fact. So if you take gamma, so it's a general statement. If I take gamma, it's not a reflection statement. A discrete subgroup of GLV, which is strongly irreducible. So strongly irreducible means that all finite index subgroup of gamma are still irreducible. So are irreducible subgroup of GLV. Then, no, sorry. Then there exists a unique ohm mean. So there exists a unique ohm max. So as their name suggests, these are gamma invariant properly convex. I should say that gamma preserve properly so I have one invariant properly convex open subset. Then there exists a minimal and a maximal invariant properly convex open subset such that for every omega, so properly convex open subset gamma invariant, we have omega, which is between omega min and omega max. So there is a minimal and there is a maximal invariant subset. Okay? Okay, so I want to manipulate omega min and omega max. There will be the, I think, the main stuff now. And so what I think is the key proposition is the identification of omega min in the case of reflection group. So by identification, I mean the fact that we know the fundamental domain for the action on omega min. So I put some hypotheses to be in a good place. So I take W irreducible and large. So it means not affine, not spherical. I take rho W representation, so as a reflection group. I take V alpha, so I recall it's the kernel, there's an intersection of the kernel of the alpha S. I assume that this is trivial, so the group is reduced. And I assume that VV, which is the span of all the VS, is equal to the whole space. Okay? So this is my standard assumption from now on. And this is the important case. So the other case, you can do them by n, basically. So this implied, so I explained that this, so V alpha equals 0 and VV equal to V implies that the representation is irreducible, but in fact, it's strongly irreducible. I won't explain that, but it's not hard. So I have an omega mean and an omega max. Okay. And in that case, so I take the same notation than for the experiment. I take D to be the projectivization of the convex hole, the cone convex hole of the Vs for S in big S. So this is a cone in a cone, sorry, without an accent in English. Cone in V. And so this is inside P of V, okay? Okay, I take delta flat. Delta flat is delta, and you remove the point on the boundary of omega v. So delta intersected with omega v. Then the closure of omega mean intersected with omega v. So what's happened in omega v is gamma delta b, delta flat intersected with D. So in other words, delta B intersected with D is the fundamental domain for the action of gamma. So gamma in this notation, sorry, I did not say it, it's rho W. The action of gamma on, so omega mean. So I put it closed, but I want only the what happened inside omega v. Okay, so this statement is a generalization of the statement inside the experiment where I told you that this fact, okay? I told you here, fact, this is a fundamental domain. Fact, this is a fundamental domain. Okay, so in dimension 2 with a triangle, it's easy to say, okay, it's obvious that this is going to be a fundamental domain. In any dimension with any convex invariant, it has nothing obvious. Okay, so dimension 2, hyperbolic space, triangle, you can do it by hand, basically. You just draw picture, make a nice, I don't know, recurrence on the length of word or something like this, and you will get it. But in full generality, you can't do that, okay? Or at least I can't do that. Okay, so, and this is, so I stress that here, for the moment, there is no convex compact in this statement. This statement is valid for any reflection group, okay? This statement is for any reflection group, any. We have W irreducible and large, and we have these two hypotheses, but these hypotheses are basically the main. Okay, the Coxeter group we really want to understand are exactly those one. Okay, the reflection group we want to understand are exactly those group. Okay. So let me first state a corollary. The corollary is that, so I re-say the, it's another way to state the main theorem. So if we have the key proposition, corollary of the key prop is that the action of rho W on omega v is convex cocompact if and only if delta flat intersected with D is compact. The delta flat is just delta intersected, D is compact. D is just a polyhedral cone. It's an image of a closed polyhedral cone to the projective space. Delta is compact, so the only thing is to check that delta intersected with D is included in omega v. In other way, it's saying that delta intersected with D, if you go to the boundary, then you find nothing. Okay, so this is just a restatement. I should put naively here, to be perfectly honest. Okay, so lemma, that it is in order now, is to state that this condition, delta intersected with D intersected with the boundary of Ongvin is empty, is equivalent to the Cartan matrix satisfies the condition of the main theorem. Satisfy no AC and no ZT. Okay? Any questions so far? So I will explain the easy way of this theorem. The converse is not very complicated. Okay. It's proof. So suppose that A satisfies IC. And I will give you a point inside the intersection, delta, D, and the boundary of omega v. So in that case, by assumption, I have I and J included in S, such that I is orthogonal to J, and Wi and Wj are infinite. Okay, so by taking I and J smaller, I may assume that they are irreducible. Okay. So I and J are, so if I take the Cartan matrix of AI, then it's of type either negative or 0. Same for IJ. Okay. So in any case, I have, so I will just take, in fact, I will just need xi. So I take xi to be the Perron-Frobenius vector of AI. Okay. And I take, so I take the same notation than on Monday, but it's not the same guy, but it's close. So I take x good to be the sum over the I in I, E, x, E, V, E in So xi is a Perron-Frobenius vector. So this is strictly positive. Vi is Vi, and so by definition, this is in D. I can stress it by put it in another color. So this is in D. Okay, but now I will check that X good is also in delta. And at the end, I will check that X good is on the boundary. The projectivization of X good is on the boundary. So I check that first that it is in delta. So I need to check that for every S, alpha S of X good is negative. Okay, so if S is not in I, then alpha S of X good is the sum of X I alpha S VI. Okay, so Xi is positive. Alpha S of VI is negative. So this is because S is not in I. Okay. And so I have this sum of non-positive numbers, so it's non-positive. Okay. Now, if S is in I, then alpha S of X good is, so it's a computation we already did last time. So it's the same at the beginning, but now I can't say that all these numbers are non-positive because one of them is equal to 2. Only one of them, but there is one of them which is equal to 2. And so maybe it's the X, so it's for Vs, alpha S of Vs is equal to 2. Okay. And maybe XS is very, very big. Okay. So I can't say that this number is negative just like this. So I need to use something, and the thing I want to use is the Perron-Frobenius stuff. Okay. So what did I say? I say that this is the sum of I of xi a si, my Cartan matrix. And so, in fact, this is just a I, restricted to I, times the vector x good, and taking at the row S. And since my matrix is of negative type, so if it's of negative type, then the answer is strictly negative. And if it's of 0 type, then the answer is 0. So in any case, this number is less than 0. And so this came from the fact that since AI is of type, so negative or 0. Okay, so I get that X good is in delta. So to be perfectly rigorous, the projectivization of X good. That I should write, don't like this notation. Okay, now I need to check that this is on the boundary. Okay, so how do I do that? I do that by using J. I haven't used J for the moment. So I take a small J in big J, and I look at alpha J of X good. Then alpha J of X good is the sum for I in I of xi alpha J of Vi. But this is equal to 0 since I is orthogonal to J. So this is equal to 0, which implies that sigma J of X good, so the reflection of X good, is equal to X good. And this for every J. So this gives me the fact that the stabilizer of X good contains the group WJ. But this group is infinite. Okay, and the action, remember, the action of rho W on Ohmvin is proper. This action is proper. So the stabilizer of point inside omega vin are finite. So it means that X good is inside the boundary of omega vin. Okay? So in particular, delta intersect with D intersect with the boundary of omega vin is not empty. Okay? Any question? Okay, so let me just explain a bit how it works with if it satisfies. So we have done when A satisfies AC. Now let's do when A satisfies ZT. So it's it's similar, but there is a slight difference. So I have T such that AT is of 0 type. By taking it smaller, I may assume that T is irreducible. So I take xt to be the Perron-Frobenius vector of AT. And I set X good, as usual, to be the sum for T in big T of xt Vt. So again, this is positive, this is Vt, so this is in D. Okay, or the projectivization is in D. Now, for the same reason, you will have that if S is not in T, then alpha S of X good is going to be negative because it's a sum of, it's non-positive because it's a sum of non-positive number. If S is in T, then alpha S of X good is going to be, so you will get the S row, the S entry of ATXT, but this is equal to 0 because we have a 0 type. So x good is inside delta. So projectivization is inside delta. And now we read again this. Here we have 0. We don't have negative like last time. So this equality to 0 is equal 0. Give me that the stabilizer of x good contain the group WT. Okay, last time my element was not invariant by WI. It was invariant by WJ. But this time it's invariant by himself, WT, which is an infinite coxeter. So for the same result, it gives me that x good is inside the boundary of omega bin. So it gives me that delta intersect with D, intersect with the boundary of omega bin is not empty. Okay. So it's the easiest way, but it's the easy way, but there is not a big gap between the easy way and the hard way. They are close together, and if you have understand the easy way, then the hard way is not hard. So the reciprocal is, I just say it's more technical, but it's around the same idea. So I don't give the proof, but it's not very different. Okay. Are there any questions? So I try to explain the key prop. So I recall, because I can't show you that much on the same screen. So I recall, but without the hypothesis. So the question is, what is the fundamental domain for the action of my group gamma rho W, which is rho W, on the minimal invariant convex subset? Okay, so it means that omega mean, if you intersect it with, so this delta flat is the fundamental domain. So delta flat, don't forget, is the fundamental domain by Weinberg work, fundamental domain for gamma acting on omega Wien. Okay, so what I'm saying is that the intersection of this set with omega mean bar is D intersected with delta B, delta flat. Okay, so there is 3 steps. You stop me whenever you want. Lemma A, which is that the identification of omega max. So in fact, the maximal invariant subset, we know it for a long time, it's omega Weinberg. Omega Weinberg is the maximal invariant subset for the reflection group. Lemma B, okay, lemma B can sound strange, but it's an expression of omega mean using only D, not using delta. And an intersection. So it can sound a bit strange, but Okay. Lemma C is that if you take the orbit of delta intersected with D, then you always stay inside this set. Okay, so these are the three statements. So what do you see? So inside these three statements, so A, you kind of don't see why it is there, okay, because it's remark. B plus C, if you have lemma B and lemma C, then you have the key prop using basically only or almost only set theory. I mean, it's just a question of inclusion and stuff, okay? Maybe there is a delta and well, even delta and delta flat, the difference is the intersection with omega mean. So it's, I mean, it's completely basic, okay? If you have B and you have C, then you have the key prop. You just use the intersection with delta and stuff like this, okay? I can come back on that for the question. So why is there a statement lemma A? Okay, so I don't know if I will have time, but in fact, B is the dual of A. So we are in projective geometry. So when you have a statement, you can take the dual of the statement and then you obtain something new. And once you have A, if you take the dual, you will get B. Okay. So so I want to do A first, and then we see how much time we have left. Okay. Okay, maybe one thing which is surprising is that lemma A is not in Weinberg work. And that can sound strange because you can feel that Weinberg should have asked himself the question or know the answer, I don't know. But if you proofread carefully Weinberg work, you will see he never speak, never in his paper of Hilbert geometry. He never used Hilbert geometry, he never used the metric on the convex. He's only doing things without distance, without any reference to a metric. And the proof will use the Hilbert metric. So suppose that omega max is not, that omega vin is strictly smaller than omega max. Okay, then I make a picture. So I have this is representing omega max. So my convex bin is smaller. So let's say that this is a bin. I have delta. Delta is my fundamental domain, but maybe delta is going a bit to the boundary. Okay, so since bin is not omega max, I have a point y, which is outside. And I have a point Z, which is inside delta. Okay, let's write that down. So I take Y, which is inside omega max, but not in omega bin. And I take Z, which is inside the interior of delta. Okay, well, delta flat is enough. And then I take the geodesic between these two guys. Okay, so this geodesic, since Y is not in omega max, is going to hit the boundary at some point. So Y prime is exactly the intersection of ZY with the boundary of omega V. Okay. So now I can look at the trajectory, but ZY prime inside it's a geodesic segment, but geodesic segment it's not even a line, it's not a segment. Geodesic line of omega V. Okay. And it's also a geodesic line of omega max. And since it's a geodesic line inside omega vin, I have a billiard path corresponding to that. So meaning that each time I go across delta, I came back with some element. So I have a billiard path that goes something like this. I don't know, I don't really care. So it's the billiard path. So I call it BT. The associated billiard path. So I put this geodesic line, I put it back inside the fundamental domain. Okay, it's the image of this geodesic line inside the fundamental domain. So inside delta flat. Okay. So, but I can look at this path inside omega max. And so this is the Hilbert distance. It's okay for the Hilbert distance? I should recall what is it? So the Hilbert distance of so by just the triangle inequality, meaning that the distance between z and y prime is bigger than the distance between omega max and my billiard trajectory. Okay. But this distance inside omega max, this distance is finite. So this number here is finite because it's a given number. So it means that this quantity is bounded. So it means that BT accumulates somewhere inside delta. So I have, so what does it mean? So it means that I have B, I have the subsequences Tn, such that if I take the distance between omega max so this is my element of my geodesic. So this is the inside. So this element, so I take gamma n such that this guy is inside the geodesic zy, so zy prime in fact. So Tn is going to infinity. So this distance is going to 0. Okay. So if I just, so gamma n is an isometry. So what I get is that btn minus 1 of right prime, this is going to 0. Okay. So we say that this is going to accumulate on a point inside. So this sequence is btn. So I came back to the picture. So the btn are going to accumulate somewhere around here. So b infinity is somewhere here. Okay. And the sequences gamma n, so gamma n minus 1 of y prime is also going to be infinity as n goes to infinity. Okay? But gamma n y prime is inside the boundary of omega vin. Okay? And b infinity is inside. So it's, and this is closed. Okay? And b infinity is inside omega vin. So this is absurd. I mean, gamma n minus 1 of y prime cannot convert. Okay. So any question? I think the Wi-Fi is back. Okay. Okay. So maybe I just explain quickly lemma B, and then we say it's good. And yeah, okay. Lemma B, and I will just say one word. So lemma C is an old stuff, so I won't explain it, but I can say which old stuff it is. So lemma B, we say it's the dual of lemma A. So I just explain briefly. So if you have a reflection group, then this is the data. Reflection group is basically what you have is the data of this alpha S of NVS, which are element of V star times V. And you have a Coxeter polytope, which is whose underlying space is this intersection of alpha S negative. And so you can take the dual. Once you have a reflection group, there is also a dual group, so the dual reflection group, which given, so what will play the so what is going to be, so Vs now is going to be played by Vs. So now Vs, I will see it as a linear form on V star, on V dual. So it's going to be an element of the dual. And alpha S is going, so it's alpha S is an element of V star, of course, but now I see it, rather than seeing it as a linear form, I see it as a vector. Okay, and so delta star, what is delta star? The dual of the dual. So what is the fundamental domain in that case? The fundamental domain in that case is the intersection so it's the linear form phi such when you evaluate them on Vs, the answer you get is negative. So this is, in fact, it's the dual of the cone generated by the Vs. So it's the dual of D. I mixed thing with a dual, with what is in the projective space and what is in the vector space. But so the thing is that the dual, so the fundamental domain, so delta star, is the dual of D. Okay. And what we get, what we say is that omega max, so omega max for, I say rho, is omega vin. So it's the union, modulo the interior stuff, it's the union for W, for gamma in W of the rho gamma of delta. Let's put, I put the flat. And the dual of omega max, rho, is going to be the omega min of rho star. Okay, so you play with that and you will change this union into an intersection, and the delta is going to be changed in D, and so you will get the statement of lemma B, which is that omega min is an intersection. So this intersection came from the dual of the union is an intersection, and the dual of delta is going to be D. Okay. So you write things properly and you get what you want. And lemma C is the lemma of CAC. So it's a lemma of CAC, so from the 60s, 70s. So CAC context is a special reflection group. It's the TITS representation of a Coxeter group. But it goes to its generalization is painless. I mean, there is no new idea. You just take back its generalization to any reflection group is painless. I mean, you just reproduce the proof and it works. I mean, there is nothing to do. Okay, it's not something hard. There is no new ID to put there. Okay. Okay. So I think I'm done, and time is over modulo the technical issue.